We saw quantum error correction last time, which was the problem of transmitting qubits on a channel where noise was present. Today, we are going to see a very, very similar problem, though it is going to be a very different problem, right? And we have talked about it. What is cryptography, or what are we supposed to do in cryptography? We are supposed to transmit qubits or bits or message in the presence of adversary. This is the important difference. Here, there is a person or a computer sitting who can watch our transmission. In general, the two parties commonly are known as Alice and Bob. They have a channel, they want to pass some messages. Unfortunately, there is a person sitting here, and generally the person is called Eve. The problem is Eve is malicious. And Alice and Bob want to make sure that whatever message they pass is not intercepted by Eve. Eve doesn't understand what is the message sent from Alice. Obviously, this had importance in Second World War and things like that, when allies or let's say Germany wanted to pass messages to Italy or something. But even in today's time, especially in today's time when there is so much communication between computers and everything, you want to make sure that your data, your message is not intercepted by someone else. And this is the problem of quantum crypto. This is the problem of cryptography. When a quantum computer is in place, when you want to transmit qubits, when you want to transmit through quantum computers, then it becomes a quantum. This is secure transmission in the presence of an adversary. There are two general ways in which this thing is accomplished generally. One is called the symmetric key encryption. Just the two terms, encryption and decryption. Since we want to send a message which is not, which cannot be understood by Eve, the tactics is that whatever is your message, it is encrypted by Alice, then sent. Once it reaches Bob, Bob decrypts the message and then reads it. Just to make sure that you understand the terms, encryption and decryption, very, very normal. Now this encryption and decryption process, this can be of two ways. It is broadly divided in two ways. One is symmetric key encryption and second is asymmetric key encryption. What is symmetric key encryption? In this case, the keys. What are the keys? Encryption and decryption keys. Are almost the same. Either they are the same or one can be get from other by just a simple transformation. Now, what happens is that this secret key, this encryption decryption key, which are related to each other, very easily related to each other. If you have one, you can get another, and so on. This is not available with key. And Alice encrypts the message using her key, and Bob reads it using his key, which are almost the same. And then, since Eve does not have the key, then Eve cannot figure out the message. So the biggest problem here in this, or biggest problem with this protocol, or the biggest, I should say, important point of this protocol is to have a secret. Do you know of an encryption protocol which uses symmetric key encryption?
AES.
Right? Yeah. So AES is an implementation, right? What cryptographic protocol does it use? So the simplest protocol is one-time pen, which, if you think about it, is not very difficult and very obvious, but very, very secure way to transmit a message. Suppose my message is a string of length n. M is element of 0, 1 to the power n. I can obviously write any message as a binary string of some length. Let's say this is my message. Then I pick a random key, or the secret key. This is going to be the secret key, which will be shared between Alice and Bob. In this case, their key is exactly the same. And then what will be the encrypted message? What will be your guess?
M XOR R.
Sorry?
M XOR R.
Right. It's simply the encrypted message, let's say code word CI, the ith bit is going to be MI XOR RI. And why is this a good encryption? Why did we think of XOR? Anyone?
Because it can be easily decrypted just by taking XOR again.
Okay. Okay. The question is, why did we use XOR? One thing, obviously, that it can be decrypted easily. But then, if that was the only criteria, then we can just send the message. If we don't do anything, then that's the best message to be decrypted, right? We don't. The other person doesn't have to do anything, right? So what is this other property? What is this security property which makes XOR very useful?
Without the key, we cannot guess what was the initial message.
Yeah. So very good. So the point is that RI hides MI intuitively. More importantly, if you go into slightly more detail, you see that remember CI, the message which I sent was MI XOR RI, and knowing CI does not tell anything, or you can get MI with probability just half. With half, you can guess any message, right? Any ith bit you can guess with probability half. You can just toss a coin and say, oh, my MI is 0. So you can always guess MI with probability half. Knowing CI, this probability doesn't change. Still, even if you know CI, since RI is completely random, MI could be CI or not of CI. In that sense, XOR is very, very precise or very good way to hide your. If someone does not have RI, if the adversary does not have RI, they will have no CI. And this is the simplest cryptography protocol. It is unconditionally secure. There are no assumptions we have to make to say that this is secure. This is definitely going to be secure if the secret key is not exchanged, right? This is the simplest cryptographic protocol. The problem or you could say the most important point about symmetric key encryption is the existence of a secret. If you use, sorry, there was a question. Okay. The most important issue with this is that you can show that if you use the same keys multiple time, same key multiple time, actually there are ways to attack this crypto system. In an ideal world, you would use a different secret key every time you want to send a different message. But that's kind of prohibitive, right? This is, in some sense, this takes us back to the original problem. We had two parties. They wanted to share, they wanted to send something, but how will they share the secret key? They can't send it. The channel is insecure. If they want to share a secret key beforehand, they will have to share a large number of secret keys, depending on all the messages they want to send in the future. That way, I'm not saying this is prohibitive, but in the sense this is a problem. This is not very efficient. This is the problem which people say exists with symmetric key encryption. The simplest example of symmetric key encryption is not that. Next, another way is asymmetric key encryption. And in this case, obviously, the encryption and decryption keys are quite different. And I'm sure you know one example of asymmetric key encryption. Can you give me one? This is also called public key cryptography. None of you know example of a public key cryptography protocol?
RSA.
Right, good. I'm sure everyone knew that. How many people have not heard of RSA? Raise your hand if you have not heard of RSA. That's what I thought, right? So everyone has seen RSA. This is the example of public key cryptography. And now if you remember RSA, you would see that you had a message, you raised it to some power, and then you had to kind of raise it to its inverse to get the message back. In some sense, the encryption and decryption key were quite different. That was the reason why it worked. And if someone tells you beforehand that such a protocol exists, it seems surprising that you have a public key and still you can do cryptography. It seems magical, but obviously it is possible. RSA is a good example. All of you know that. But the problem, or at least the problem from a quantum computer scientist point of view, is that this public key encryptions, they are not unconditionally secure. That means, other way to say it is that they are conditionally secure. They are secure based on assumptions. What are the assumptions? Generally, what kind of assumptions are there which make RSA and other public key cryptography protocols secure? Come on, you know that. Let me pick a person and ask. Can you hear me?
Yes.
Yes. Okay, so should I pick a person, or someone will tell me why, on what principles, or what principles are used to say that RSA is secure?
The properties of hash function use that it has no collision and it's hard to compute and all those things.
Okay, right. What
Um,
about RSA?
Finding prime factors is hard for large number, a very large number.
Right. So factorization. In all of these protocols, what we use is that some computational problem is hard. For example, for RSA, it is hard to factorize a number, and that makes it difficult to build this crypto system. That is the reason why Eve cannot intercept the message from Alice to Bob. The problem is that using quantum computers, we can solve the computers, we can solve these computational problems. Obviously, we know Shor's algorithm that tells us that we can solve some computational problems on which these encryption decryption techniques rely on. What is the way out? Quantum cryptography is a big subject. One direction is to find different computational problems. And base cryptography on. Base cryptographic, or I should say encryption protocols. This is generally done through lattice problems. This is one area, this is a big area. We won't go into this. This is actually, in some sense, completely classical. The only quantum part comes by saying that, oh, there is some evidence that these lattice problems would be hard to solve even on a quantum. Otherwise, the crypto systems and everything, those are done classically. These things are called post-quantum cryptography. Post-quantum in the sense that once quantum computers are in the reach of people, then we will have to change our cryptography. So once you have quantum computers, post-quantum world, what will be your cryptography? Post-quantum cryptography. And one way is this. We are not going to talk about this. What we are going to talk about is something which is very old. This is called the Bb84 protocol.
Sir, one question. In lattice problems, are these hardness provable hardness, or
There are evidences.
okay? Means these are open currently, right?
Yes.
Okay.
Again, I'm not very familiar with the recent developments, but as far as I understand, they say that, oh, these lattice problems seem hard, and that's why these seem hard for a quantum computer, and that's why we can't do it. One example is, I think one lattice problem is equivalent to dihedral hidden subgroup problem on a dihedral group, which is not abelian, and hence you can actually base cryptography, because there has been a lot of effort to solve hidden subgroup problem on non-abelian groups, and it hasn't succeeded. Then people kind of think probably solving hidden subgroup problem on dihedral group would be very hard. And there are crypto systems based on that. But again, there are much more things, and I'm not an expert on that. This is what I know, and this is what I will do. What we will look at is this Bb84 protocol. This is by Bennett and Broussard. There are too many double letters in these authors' names. I might be missing a few. I'm sorry for that. This was obviously discovered or presented to us in 1984 to the scientific community. Again, this was a surprising result, but very beautifully, it gave a way to distribute a secret. This is called quantum key distribution. Remember, for the symmetric key cryptography, not the asymmetric one, but the symmetric one, the main problem in the one-time pad, let me just say one-time pad, to perform one-time pad, the main problem was presence of a secret. What does Bb84 do? It uses quantum mechanical principles to share a secret. I started with the objective of passing the messages between two parties, say Alice and Bob. Now remember, our task is slightly different. What is the task now? We have two parties, Alice and Bob. Again, they have a quantum channel. They want to have a protocol in between. There is Eve sitting. They want to have a protocol so that by the end, they have a secret random key. Obviously, Eve should not have information about it. This will be used, the secret key will be used with one-time pad to transfer messages later. So the protocol I'm going to describe will not have any messages. The only objective is to exchange or to agree on a secret. This is the only thing which we want to achieve in this protocol. Then we have one-time pad and we can do the cryptography. The Bb84 protocol works because of two quantum mechanical principles. One you have seen a lot of times, no cloning theorem. I don't need to describe it to you in detail. You already know it. It says that very informally, you can't copy qubits. I want to emphasize this, that this basically means, it doesn't mean that from zero, I can't create 0, 0. If I know the state 0 and I just want to create 0, 0 from 0, that definitely can be done. What it says is that if I have some state psi, whose information I don't have, whether psi is this state or that state, it is not possible to convert it into psi. I want to emphasize it because I was checking major quiz and I saw that some people still in their protocols copied qubits. We can't, right? After this course, you should definitely be sure about this, that we cannot copy arbitrary qubits like we can copy arbitrary bits in the classical. This gives rise to many problems as well as many solutions in quantum computing. This is one where we use this principle to solve our problem. The second principle is that measurement disturb the state. Whenever some state is given to you, you don't know which state it is, and you measure in some arbitrary basis, that disturbs the state, which can later be detected. I'm not going to be very formal about it. This has been captured as a theorem in Nielsen and Chuang. You can read there if you want. But intuitively, it is clear to you. If you look at the third postulate, it clearly says how the state changes once you perform a measure. How we use it in this protocol, that also I will show it to you. But intuitively, this principle is clear to you. You have seen third postulate, so it should be understood. Now, whenever you measure some state, but if it's not the state, if it's not in that basis itself, it will change. And then we can detect it. How we detect it, I will show you one example to this. These are the two principles, quantum mechanical principles, which are used to make this Bb84 protocol secure. Any questions till this point? Okay. Let's look at the protocol. Our objective is to share a secret key between Alice and Bob. What it needs, the protocol needs, or what we assume that Alice and Bob have, is obviously a quantum channel. But we also assume that they have at their disposal a public classical channel. That means we don't worry about who reads this channel. That is not, we assume that whatever we write here will be read by everyone, but that is not going to affect the protocol. One way to think of this is newspaper. This is the newspaper, and the quantum channel is, how I should say it, a quantum phone or something, right? When you talk to your friend on your phone, you don't believe, or you don't think that that will be heard by other people or by me or something, right? So this is the quantum channel. The objective is that you will be able to share a secret key, and if someone here, Eve, intercepts the message, we will get to it. We don't care if someone reads our message on public channel. We assume everyone is reading it. But from the quantum channel, our expectation is, or the protocol, our expectation is that if someone interferes with quantum channel, we get to know. Then we can abort the protocol or things like that. Right? I have everything now to describe the protocol. Let's look at the protocol. Before I start the protocols, how many people have seen the protocol before? Raise your hands if you have seen the protocol. Interesting. Since none of you have seen it, it will be a very, very nice, very simple application of what we have seen. A very, very simple application of quantum principles. That's what I like about it. It achieves a nice thing, which is very, very difficult in the classical case. Still, the principles it is based on are very, very simple and seems like anyone could have thought of it to start with, though we didn't. But a brilliant protocol, very, very nice. Let's see. If a very, very stupid question, but let me ask it. If Eve was not there, how would you share a secret key between Alice and Bob? Probably it's too simple a question to answer, but let me ask it anyway. Suppose Alice and Bob want to share a secret key. There is no Eve. They don't want to worry about that. How would they share a secret key?
They would just share it. I mean,
Sorry?
they would just share it over the channel and
Right. And yeah, but you would want it to be random. So let's say Alice will toss some coins. Alice will come up with a string of length n. This is going to be the secret key. She will toss coins and decide every R1 is this, R2 is this, Rn is this, and send it to Bob. Right? This is our objective. What we will do is we will transform it in a certain way so that we can keep part of it. That is the idea. We are supposed to send R to Bob at the cost of security. We will encode it so that we can at least get half of the secret key across Bob. Other way to say it is, if you want to share an n length key, we will start with 2n or a 3n length key. That is another way to think about it. Let's look at the steps. This is the secret key which we want to share. Alice will also choose randomly n other bits. R, we should think of it as the secret key intuitively. A, we should think of it as the random choice of bases. By the way, let me test your quantum knowledge. What is the standard basis for a qubit? Come on, that's
0, 1.
0. What is the Hadamard basis?
Plus minus.
Correct. This you remember, right? Now, if AI is 0, then encode Ri in standard basis. That means 0 will become cat 0 and 1 will become cat 1. If AI is 1, then we encode Ri in Hadamard basis. Or not we, I should say Alice. This is done at Alice's end. What does she do? She picks a secret key, she picks a random choice of bases and encodes every coordinate, every Ri, depending on her random choice of bases.
We had a question on midsem. This isn't this similar to that?
Very good. Right. That protocol was also another way to give a secret. This was done by Bennett in 90, the one which I asked in the midsem. This one is slightly different. This is made by Bennett and Broussard in 80. But you are right that there also the objective was very, very simple. You will see how this is different. Now AI is equal to 0, encode Ri in standard basis. AI is equal to 1, encode Ri in Hadamard basis. Then what does Bob do? Sorry. Bob will generate his random choice of basis. These are some BIs, B1 to B. And then measure the encoded qubits in in his choice of basis. That means if BI is equal to 0, measure in standard basis. If BI is equal to 1, then you measure in Hadamard basis. Now,
So one question, but what is BI over here? Which index are you pointing to?
this will be done for all I.
Oh, okay. Means
Similarly, Alice does this for all I. I'm sorry, I should have said this. For every I, Alice encodes Ri with AI. And then Bob also for all I will pick a random basis. That is why we have B in element of 0 to the n and measure for all the indices. Right? Now we have two secret keys. R if R with Alice and let's say S with Bob.
sir, one more question. Can you go back to the last slide?
Sure.
Yes. So over here, you R is a n-bit string, right? So
Correct.
if AI is 0, encode Ri in the standard basis, you mean we'll consider cat1 or cat0, right?
Right.
Okay. Okay.
Or in the Hadamard basis, we will consider cat plus or cat minus.
And express 0 and 1 via that cat plus or cat minus if AI turns to be 1.
Right. So good point. Actually, let's take an example. Right. Let's say R is 0, 1, 0 and A is 1, 1, 0. Then tell me what will be sent by LS? What will be the state which will be sent by LS?
Plus minus 0.
Correct. Because A is equal to 1, that means we want to encode in Hadamard basis. R is 0, that means this is going to be plus. Then again in Hadamard basis, I want to encode 1, I will send minus. In the standard basis, I want to encode 0, so I will send. Make sense?
Yes, thanks.
And now Bob is going to measure in his basis. Then Alice and Bob disclose their A comma B, their choice of basis, on the public classical chain. They will announce in the newspaper, this was my choice of basis. Actually, it doesn't matter whether just Alice discloses it, that's good enough. Then Bob can say, okay, just look at these indices, or both can disclose. It doesn't matter. Let's go with this, that both of them disclose their A comma B. And then we wanted to get a shared key. Can you guess what will be the shared key?
The indices on which A and B match or something like that.
Right, very good. This is going to be Ri's such that AI is equal to BI. Now Alice knows A comma B, Bob knows A comma B, they can compare their A and B. if they see that, oh, our choice of basis was same on, let's say A was yeah, let's take an example, right? We will continue our example. Remember, R was 010, A was 110, then the state sent was plus tensor minus tensor 0. Correct? You want to tell me what is B? What should we pick as B? Don't give me 001. Give me any other string except 001. What is your favorite number between 1 and 8? Sorry, or 0 and 7?
3.
3. Okay. 101. Sorry, 011. Sounds good? Now, Bob measures the first bit in the standard basis. That means, what will be the first value of S? What will be S1?
It could be 1 or 0.
With equal probability, right? 0/1 means 0 or 1 with equal probability. Now, Bob measures minus in the Hadamard basis. What will be the output?
Minus.
That means, what will be SI? S2?
1.
1. And then what about the third case? You will measure 0 in the Hadamard basis.
0, 1 with equal probability.
Good. This is what we know about S and R. Now we know that wherever AI was equal to BI, their value will definitely agree. And that will be our shape. Right? Let's not worry about the security, but this fact that in the end, they will have whatever shared key they will have the same things at the same place. That is not questionable. Definitely at the end of the protocol, they will have a shared secret, a shared random. That should be clear from this. Do I need to explain it again? Anyone raise your hand if I need to explain it again. Okay, good.
So what in case of superposition, like we have a 0 and 1 both with equal probability, and at that point AI and BI were same, then what is the shared key?
Can that happen? That is why I'm saying you should be convinced that if AI and BI are the same, then
Okay.
then we will not have a superposition, right?
Okay. Yes.
You will measure in the same basis, and then you will get a definitive answer.
Yes, I understand.
You will get a definitive answer in all cases, but the value will also. Right? Okay. If you understand now this, then let me ask a few questions to you. What is the expected length of the secret key?
N by 2.
Yeah, that's very simple, right? You pick two random strings. At half the places, they will have to agree. Right? Reason AI agrees with BI
With probability half.
with half. if AI is not equal to BI, what is the probability that Alice and Bob agree at that index?
That is also
Right.
half.
Right. Irrespective of whatever basis they had chosen, since their bases are different, that is why we chose plus, minus, and 0, 1, right? If we measure plus or minus in standard basis, it will always be half with 0, half 1. Similarly, if we measure 0 and 1 in Hadamard basis, it will be 0 with probability half, 1 with probability half. That is why it doesn't matter what was the value of AI, what is the value of BI. If they disagree, then Alice and Bob agree at ith place with probability half. It doesn't matter because we are going to anyway discard these places. These will not be part of our C. Why didn't Alice and Bob disclose their bases in the beginning of the protocol? These are just sanity checks. So that we are sure that we are talking about the same protocol, the things are clear.
Anyone could have measured that that we were sharing.
Very nice. What could have happened? Eve could have measured in bases and send the result to Bob. Right now we have started talking about, we were only making sure that this protocol works. Now we are talking about the security issues. Let's talk about a few cases. Actually, what happens is that we know that on the basis of quantum mechanical principles, this protocol is unconditionally secure. Yeah, just requires the principles of quantum mechanics to hold. This is one time when I will be on the side of physicists. Previous protocols worked, the asymmetric key protocols worked on the fact that some computational assumption was correct. This protocol instead requires that some principles of quantum mechanics hold true, and my belief would be that these are much more stronger. Quantum mechanics has been in this world for a much longer time, and even though I think out of whatever 11-12 people we have here, uh, probably most of them are computer scientists. Can you raise your hand if you are a computer scientist, if you belong to computer science department? Okay, interesting. So very half of us are computer scientists, and we would like to believe that our computational assumptions are very secure, but still at the level of uncertainty, I would say that physics assumptions are should hold true with a larger degree of belief as compared to our computation. Especially when we talk about, oh, the factorization problem is hard, or the some kind of computational problem is hard to complete. Right? That is why this is a bigger achievement. This problem, we would, since we believe in physics, we would say that this protocol is unconditionally secure. Though to show that's kind of outside the scope of the course, I also don't know the proof. After the end of the protocol, there are two steps. Don't ask me much about them. These are classical steps, classical cryptography steps: information reconciliation and privacy amplification. Once the protocol is finished, Alice and Bob are supposed to apply these classical protocols, and that makes this Bb84 very, very, I should say, unconditionally secure. Though I also don't know about these, we will not go into the details of these two, how this is done. In the rest of the time, what we will see is possible attacks, some of the possible attacks, and how they can be discouraged. This, in some sense, this shows that why we believe that this protocol is secure. We will not give a formal proof that's outside the scope of this course. The first attack is very, very simple. What if Eve copies the qubits, then send one copy to Bob, and then measure her qubits once the basis is disclosed. Once the bases are disclosed. This is something which could definitely be done classically. What stops Eve from doing this? Why can't Eve do this?
No cloning theorem.
Right, simple. Right? This was on Platon. Right, because of no cloning theorem, obviously Eve can't copy the qubits. Let's take another attack. What if Eve measures the qubits in random basis? Let's say some E and then send the measured qubits to Bob. What happens then? Is there a way to
Even
detect
then,
this?
at least, even then, we can at least find one which is anomalous. Then you know that there was an attack.
Very nice. Very nice. Yeah. What will happen is that there will be an anomaly in Alice and Bob's outputs, Ri and Si. Let's see, what do I mean by that? What is the probability that EI is not equal to AI or BI? Suppose AI is equal to BI. What is the probability that AI is not equal to AI? I should say not AI divided by, it might be confusing, AI equal to BI. Yeah. Right, simple. We have some AI BI has some value 0. I choose a random bit. What is the probability that this random bit agrees with AI or BI? Just half. That means at these places, Eve's answer or Eve will measure in a different basis as compared to Alice's basis, right? Let's say, let's take it simply that R was 0, R1 was 0, A1 was 0. That means what will be sent?
0.
0. Now, Eve measures in which basis?
Hadamard.
Correct. Because EI is not equal to AIBA, that means EI is equal to 1. Measures in Hadamard basis, then that means what state will she send to Bob?
Either plus or minus
Correct.
0.
Eve will send this state to Bob. And now Bob is going to measure in which basis?
Plus 0, 1 basis.
Bob will measure in 0 or 1 basis. Right? And then again, with probability half, he will get 0. With probability half, he will get 1. Right? That means if AI is equal to BI, then with probability 1 by 4, RI is not equal to SI. Do you agree? If AI is equal to BI, if EI also agrees, then nothing doing, then we can't help it. Eve got lucky. With probability half, Eve will have a different basis. If Eve measures in a different basis, then she will definitely select plus or minus. And then with extra half probability, Bob could fall into either 0 or 1. If they fall in 0, then great. Then actually not great. Then in that case, R will agree with us. If she measures 1, if Bob measures 1, then RI is different. That will happen with probability equal to 1 by 4. Is this probability 1 by 4 clear? Okay, I assume there are no more questions. Okay, once I know this, then can you think of the way in which they can detect the presence of Eve? It's good. That means that at some places we will have an anomalous behavior as pointed out, right? With probability 1 by 4, RI is not equal to SI. We assumed RI should be equal to SI whenever AI is equal to BI. It is not going to be there. What can we do with this anomalous behavior?
You can check RI's, I mean,
That's our secret key. How will we check?
So, can we send it multiple times?
Can we send it multiple times? What does that mean? Sorry.
Means the probability is 1 by 4. So that is a very less probability, right? Means in order to find out whether RI is not equal to SI.
See, we are not worried about the, okay, RI is not equal to SI is a problem, but bigger problem is that Eve has other parts of the key. So it is not that we are worried about this small part which disagrees between Alice and Bob, but we are more worried about the fact that Eve has some secret key. Because once we disclose the basis, Eve can check. Right? In what basis agrees with Alice and Bob, and in those bases, everything will be perfect, and she will know the key at those places. So she will know at least half the key.
Sorry, what is our objective here? To find out whether Eve has the basis or not.
We want to make sure that someone has not intercepted our communication, right?
Oh, okay.
This is obviously RI not equal to SI is a problem, because now we have a secret key which doesn't agree. That's one problem, but the bigger problem is that Eve can guess many or has access to half the secret key in expectation. And future, whenever you will want to send your secret message, she can recover a lot of it. Right? So our problem in this sense is to detect that Eve has manipulated the channel. Yes, ideas?
So Alice also has Bob's key, so she can figure out if SI doesn't match.
How does she have Bob's key? She does not have SI.
Okay. When they both disclose,
When they disclose the when they disclose the basis, she will have the key, assuming there was no E. But in this case, Bob will have a different key, Alice will have a different key. They haven't shared it, so they don't know,
okay.
right? Uh, uh,
So
Alice will
can we
believe.
send multiple copies of this initial messages that was with Alice? Means Alice knows what is the message, so he can copy it.
Mess no, sending multiple messages might anyway be dangerous, because then if I detect with, let's say I start, you send it 10 times, first 6 times I try with header mode as well as standard basis. If on header mode basis, if it comes out to be two different outputs, then I know that you want to send in the standard basis, then I know which basis to measure.
Oh.
You see my point?
Hmm.
Right? So my protocol would be, if you have 10 times, I will, and 9 times, I will try with header word basis. If all the times I get the same output, that with high probability means that you encode it in the header word basis, I will measure with header word basis. If I get a different output, then I know you have encoded in standard basis, I will measure in standard.
So can we send a dummy random key, and if we detect error, we'll start the process? Like we'll continue with this, otherwise we'll start it again and
Very
send
nice.
different.
Very nice. So you don't have to share a dummy key, because there is no original message as such. What you can do is you can disclose part of the secret key. Right? Let's say whatever is the secret key we had, we will disclose half of it. Both of them, Alice and Bob, disclose half of it on public channel. And then if the length is n, there will be many places where Alice and Bob differ. On an expectation, let's say if they started with n places, then n by 2 places their basis will agree, or this is n places secret key will agree. And then even if they share half, or let's say 1/4 of it, n by 8 places, first n by 8 places, let's say they share. And then many of these, or around n by 32 of these places, on expectation, again, these are all with expectation, n by 32 of these places will have different shared key. That means Alice and Bob's shared key will not end with high probability. And then that means if their secret key doesn't agree, that means E was present. And they have shared n by 8 places, the remaining 3n by 8 places will become the secret. If the n by 8 places they don't find any difference, that means with high probability Eve hasn't done anything with it. Then the rest of the 3n by 8 places will be there. Make sense?
So how did we get to n by 32 from n by 8?
Oh, because remember that at every place, the probability that Ri is not equal to Si is 1 by 4. Look at the top of the page.
So, but that is not independent for every I, right? Because if Eve selects with half probability the correct basis that Alice and Bob had decided, then she will, like, once she knows one index, she'll know all the indices.
No, that
I
is
mean,
not correct.
I mean, Alice and Bob decide that like one would be the standard basis and zero would be Hadman. So, like with half probability, she will choose the correct basis, and if she measures, then she has the whole string, right?
No. E is again a string of length n. Why will she measure everything in the same basis? You are saying that Eve will measure all the places in either header mode or standard basis.
Like, okay, I think I
So yeah,
got
so
it.
that's why I think what Deepajit pointed out in the beginning, I think this is an important point. Remember, for every place, we have a different choice of basis. Right? If my secret key is R, I have R1, R2, Rn. AIs are all can be all different. And here is an example, right? For every place, it's just independent. Every place is encoded completely independent. There is no relation between that.
So that basis, like choosing that basis depends on AI, and Eve already knows AI and BI both. So I'm saying that once she knows AI and BI, the like and if they're equal, for example, if she gets one, then with half probability she'll measure in Hadamard basis and with half in standard basis. In if she measures in the standard basis, then it's
No,
wrong.
but
But
when she measures the qubit, she does not have AI and BI, right? They disclose the basis only after Bob has gotten the message, right?
okay, yeah, okay.
That is definitely, that is why I asked this question, right? That why don't they disclose in the beginning? Why didn't A and B disclose the basis in the beginning of the protocol?
Right.
They will
So by
only
disclosing the
disclose.
basis, you mean disclosing A and BI, like
Correct,
AI
correct,
and BI.
correct,
Yeah.
correct. That they will do once Bob has gotten the qubits.
Yes.
Before that, they cannot disclose the basis.
Okay. Yeah, that makes sense.
Okay, and then actually, anyway, even if this was not independent, this is just expectation calculation. So n by 32 to get from n by 8 to n by 32, you really do not need independence at every place. This will just follow from linearity of expectation, which does not require independence between the quantities. Anyway, that's more of probability and not this, but so yeah, there will be a lot of places where their secret key will not agree, where they have disclosed the secret key. They will find out, oh, Eve has Eve has gotten the message. Eve has manipulated the channel, and then they can abort the protocol. That's that is the Bb84 protocol. Any questions?
Sir,
Yes.
sir,
Yes.
so I just had one confusion. So the random choice of basis is it same for all i's, or like one I can have 0 plus and the other I can have like a basis of y and 0?
You saw, right? We did this experiment. So A and B were different, right? Is this your question? Can AI and BI be different?
No, like for like for I is equals to 0, we have 0 and plus basis, and for I is equals to 1, we have 0 and the basis of poly y matrix. Let's say.
Yeah, no, that is not for I equal to 0 or 1. That is for AI. You are getting confused between, see, the I is an index. I is a coordinate which goes from 1 to n. for every coordinate, if AI is 1, then we use the header mode basis. If AI is 0, then we use the standard basis.
Okay, okay. So our choice of bases is same for all places.
No,
Like
because
we have a choice between 0 and plus.
right. So Alice can when Alice tosses her coins to decide A1 could be 0 and A2 could be 1. That means the first basis, first qubit, she will encode in standard basis. Second qubit, she will encode in header mode basis. Sorry,
Okay, okay. And that is same for all places, right? So it's not as if for first place she's deciding between 0 and plus, and then and for second place she's deciding between another choice of basis.
No. But those standard and header mode bases are fixed.
Okay.
You can do it in a different basis, it won't change anything. You are saying that depending on the position, you have different choice for basis. In the first position, you will use standard header mode. In the second position, you will use some basis B1 and B2. That's what you are saying, right?
Yes, sir.
That won't change anything. That won't change the security or anything. So there is no point making the protocol more complicated. Because this protocol will anyway be public.
Okay.
Right? If we say that, oh, at the second position we are going to use this B1 and B2, that will be known to E. Then there is no use. You can, yeah, that one question might be that you can say, oh, at the first position, I might toss a coin. If the coin turns out to be head, then I will choose between standard and header mode. If the coin turns out to be tail, then I will choose between B1 and B2. But I think that will make the protocol much more complex, and I don't know what will you achieve with that. Okay.
Okay.
Okay, that finishes this lecture.